So the last speaker of this morning session is Professor Chun-Bong Park from KIAS, and he will tell us the formation of the morphology, star formation activity, recent cluster-centric radius relation. Please.
Thank you. It's so nice to come back after the previous cluster meeting held in 2019, 6 years ago. Very happy to see some of the people who were in the previous workshop. So finally, this is the first theory talk this morning. Maybe there will not be many theory talk in this workshop. This is a talk about the emergence of some of the empirical relations we found in nearby clusters using HR5 simulation. So this is work with Song Hong and Jae Lee and many people in our HR5 collaboration. So let me briefly review the observation that I'm going to address in this talk. And as a function of cluster-centric radius, it shows you that there is luminosity dependence. Okay, so if for the brighter galaxies, the fraction of early type is higher. And also, as a function of cluster-centric radius, if you again measure the fraction of early type galaxies outside the cluster virial radius, you can see the fraction is independent of the local density. There is a lot of increase in local density from 10 times the virial radius to 1 or 2 times the virial radius. But you can see this icky early type fraction control is horizontal, so it's independent of density. But there is a strong monotonic dependence on the distance to the nearest neighbor galaxies. So when your neighbor is early type, you are likely to be early type as you get closer to that neighbor. If your neighbor is late type, it's the opposite story. So outside cluster, the field galaxies, this is the one, and inside cluster, you see completely different dependence. So there is a strong cluster-centric radius dependence of cluster galaxy morphology. So we want to understand what's happening and when this relation is happening. For the star formation, something similar happens. So again, as you approach toward the center of cluster, outside cluster is more or less independent of local density. It only depends on how close your galaxy is to your nearest neighbor galaxy. So when your neighbor is early type, your late type galaxies, the color is monotonically redder as your galaxy approach late type, early type galaxy. But inside, it's similar. So now you are inside the virial radius, and again, there is more impact from your nearest neighbor early type cluster galaxy. So, but it has some slope. So there is some impact from cluster hot gas, but it's mostly from the hot gas of cluster early type galaxies that is affecting your star formation activity. Similar in the short time star formation data. Okay, so I guess this was published 16 years ago, so maybe some of you already know this. So the question is, when this relation, the dependence of luminosity and morphology and star formation activity on cluster-centric radius appeared in the history of the universe, and what was the reason that this relation exists in galaxy clusters? So we used Horizon 5 simulation, which is a flat lambda CDM simulation using hybrid version of MPI plus open active version of Ramses, and the simulation box size was a gigaparsec, and there is a zoom-in region of size gigaparsec by about 120 by 120 megaparsec, and its resolution is, the post resolution is about 1 proper kiloparsec, and it shows the distribution of dark matter and gas and stars, and this bar is 100 megaparsec. Oh, I cannot go back. Maybe. It's okay, yeah. I'll be careful. It's okay. Yeah. So I skipped one slide, but it doesn't matter. Okay, so in the HL5 simulation, which stopped at G equal 0.625, unfortunately, we ran out of computation time at 0.6. So at this epoch, we identified 162 galaxy clusters having mass greater than 5 times 10 to the 13 solar mass, thinking that they will reach 10 to the 14 at Z equal 0. And then we followed the main progenitor of this most massive cluster galaxy in each cluster, and then inspected all the nearby galaxies around these most massive cluster galaxies. And this is one of the examples. So the blue ones are the future cluster mapper, and this is the video radius, and this is 0.1 and 0.3 and 1 times the video radius. Okay, here is the result. Here I'm showing you the stellar mass and asymmetric parameter and searching index and specific star formation rate as a function of normalized cluster-centric distance at a few redshift. So this is the final impact of this simulation, and there are high redshift data like this. So let's look at the searching index first. So at high redshift, this median searching index at different cluster-centric radius is almost flat. So there was no morphology density relation. But starting from sometime around redshift 2, you see this curve is turning up near the center, and after redshift 2, it develops more clearly. Okay? But you can see that it's only the center that you see these spheroidal shaped galaxies. Okay, so you can see that morphology cluster-centric relations start to emerge at around redshift 2. Okay? And then it's well established by redshift about 1.5 and 1 here. So that's the impact. But I have to say that the evolution of this morphology and also star formation activity depends on the subjective physics of the simulation. So the exact value on when this relation starts is not too important. Okay? But at least given the subjective physics we adopted, this is the one example of the epoch of emergence of this relation. Okay, so now let's look at the specific star formation rate at different epochs. And again, there is a flat median relation of specific star formation relation as a function of distance. And then after about redshift 1, starting from about redshift 1, you start to see this is started to drop. And that's the epoch when the mass of the central galaxies start to reach 5 times 10 to the 10 solar, sorry, 10 to 12 solar mass. Okay. So at redshift 1, the average mass of central galaxy, which is about what 11.5 solar mass, and then these galaxies orbiting around, they start to get quenched. So you can say that the specific star formation rate and the cluster-centric density relations start to emerge around redshift 1 in our simulation, and it's well established below about 0.8. Okay, so I have such a short time today. One thing I want to address to understand what's going on, as a function of radius, I'm showing you the sum of the galaxies that located near the central part of the cluster. Okay, and this line, each line shows one galaxy, the position at g equal 1 and position at g equal 0.6. So this means that this galaxy was outside the virial radius and then inside the 0.1 times the virial radius at g equal 0.6. So all the small mass galaxies are the ones that came far from the center and they merged. But the massive ones are those that were already sitting near the central region between g equal 1 and g equal 0.6. So you can see this. And also, if you see this, the galaxies that came outside the galaxy, outside the cluster, and came into the central region, they are the disk galaxies. But there are many galaxies near the central region that has high search index, the spheroidal shape, and also the asymmetry parameter is big. So there is a lot of interactions going on here, which makes them somewhat irregular or spheroidal. Okay, because I have very limited time, let me summarize. So we use HR5 simulation to study these empirical relations, and we found that this morphology cluster-centric radius relation started to develop between g equal to 3, and that is well established by g equal 1.5. And I was quite surprised that the co-Ishtar's talk, just previous my talk, is supporting this. And also star formation rate to cluster-centric radius relation, we found that it starts emerging at g equal 1 and proceeds to low redshift. Okay, thank you very much.
Questions? So can you go back a few slides? Yes. So I don't quite see why there's a connection between the central galaxy growth and the overall star formation, specific star formation rate decrease.
Why did I relate with this?
So you seem to imply the growth of the top panel, top row, and there is some connection to the other panel.
Right, so when the stellar mass of central galaxies reaches the stellar mass of about 10 to the 10.5 to 11, okay, so that's the critical mass. So their total mass is about 10 to the 12.5. And at that point, the hot gas produced inside is not able to escape. So they start to develop hydrostatically stable hot halo. Okay. So that's the beginning of star formation mentioned.
You mean a hot halo within the cluster region?
It could be just one galaxy at the center, the most massive one, but there could be more than one. And as their mass reaches 10 to the 12.5 in total mass, then each of them has their own stable hot halo. Okay? So So as they interact with other cluster galaxies, they can catch the other members. So.
Other questions?
Thank you. So you mentioned very briefly that changing the subgrid physics changes the morphologies. Can you just give a bit more detail? So in which way?
I mentioned that when I was describing specific star formation rate, not morphology. Okay? So the star formation and also feedback is a little weak in our HL5 simulations. And that may be why the onset of this relation is a bit late. We think if the feedback was higher in our simulation, this appearance of this relation will probably shift it to a little higher redshift, but not too much because the growth of the total mass of galaxy is very important. So maybe a little bit shifted to higher redshift. And also important message is that the morphology relation and this specific star formation relation are not necessarily should appear at the same epoch. They are different things. So they can appear at different epochs.
Okay, I think for the rest of the questions, please ask Chambon on the Slack. And let's take this opportunity to thank all the speakers. Thank you.